Hi, I'm Bharat. My project for this course is about fine-grained mobile app testing and security detection. What is fine-grained mobile app testing and security detection? When a developer builds an app and wants to publish it to users, they are subjected to a variety of questionnaires and terms and conditions, after which they submit their app for review to an app store. App stores perform a series of strict tests on each submitted app before publishing it on their storefronts. Even after such procedures, this is what we get to see. Every one of the articles shown here is from the last 2 months alone. It is becoming harder and harder for testing apps, with developers making use of code obfuscation, URL embedding, and other techniques. Although the request made by an app to a remote server is something we can capture without having to go for reverse engineering techniques. That is where this project comes in. What does this project do differently? Just like it's shown in the diagram, a proxy server is set up between the phone and its internet connection to capture all of the network requests made by it on the app by the app running on it. This collected network data is then analyzed to determine if a given app is malicious or not. The whole process will become much clearer in the demo segment of this presentation. Methodology. These are the three segments to which I am splitting my methodology. Starting with the virus share dataset. Earlier, this project was supposed to use the Malgenome dataset, which did contain network flow data in it. But unfortunately, it is no longer available. Therefore, we had to opt for the virus share dataset. The virus share dataset is a massive open source dataset which provides us with executables of all identified malware samples. Aggregating network flow data. The executable Android apps from the virus share dataset were run on an Android emulator while it was connected to a proxy server. This is how I collected all my data to train my model. This process was repeated for several apps until I had enough data to work with. Training a classifier. All this collected data was fed into a fast AI tabular data learner. For my deep learning segment, I made use of Fast AI, a library built on top of PyTorch, which provides very easy access to state of the art results very quickly. After running about 25 epochs, I ended up with a 97.8% of accuracy and a validation loss of 6%. This here is the architecture of the model FastAI provided me. The embedding part seen here is the 7 inputs I feed into my model, and the part here is the architecture provided by FastAI. And this is a graph plotted by the library for loss versus learning rate. Let's go to the demo now. Let's start with creating the network flow CSV file for a random app from the virus share dataset. So this is the empty CSV file, and now the proxy server is running, and we are about to get a virus share APK, and now the app is installing into the Android emulator. Opening up the app, and I'm speeding up the process of using the app because that will take really long if I try to show it in the video. So this is how a malicious app usually looks. It redirects you to random web pages. It adds a lot of random things on your home screen, and in the side you can see all the amount of network requests it's making, and it's all getting saved to a file. Now I've got the network data I want. Now I'm running the file through my inference Python file. Now, every request inside that file is inferenced through the model, and an average score is generated and decided whether it's a malware or not. And as you can see, it accurately predicted that app was 100% malware. Now, to verify that non-malware apps also work well, this is the script for inferencing. Now let's check out a app. Check out an app which is not a malware. For this example, we'll be using Google Maps. And as you can see, Google Maps, it predicted as 99% of not malware. So most requests in Google Maps weren't identified by the model as malware. Now we are trying out YouTube. Same goes for YouTube. About 98% of the requests made by YouTube are not malware. Now let's try with another malware app which is a part of the data I collected. Even this one shows up as 99% of malware, and which is again correct. Potential work in the future. The results you just saw from the demo was only from 20 apps worth of training data. Imagine how much smarter this model can become if trained with all the samples from the virus share dataset. This could be a potential improvement to the current industry standard for dynamic testing. Also, exploring if training a separate model for each type of HTTP request, that is, get, post, or put, makes any difference to the overall performance, because get requests usually do not have a request body, and post requests do not always have a response body. Avoiding all these confusions in the inference might actually make it faster. Summary: traditional testing methods are getting harder and harder, with apps becoming harder to reverse engineer. Hence, the network analysis approach is the one to go for, since the network analysis approach needs no access to the app source code. The deep learning model was able to predict malicious requests at a very impressive accuracy. Conclusions and outcomes. The trained model was able to identify a completely new malicious app accurately. The model also does not fail in identifying non malicious apps. This proves the existence of a pattern in network requests made by malicious apps from those made by genuine apps. Thank you.